So this tutorial is on bilevel pressure control. It's a mode of ventilation that's been around since the turn of the 21st century. It has a number of different monikers, the most popular being bilevel, BiPAP or Bivent, but they all more or less describe the same mode of ventilation. Tutorial 28. Modern modes of mechanical ventilation. This tutorial is about bilevel pressure control. Welcome back. Previously I discussed volume guaranteed pressure support ventilation, otherwise known as volume support. I explained what this was and how to set it up. I also discussed clinical situations in which volume support is useful. Finally, I discussed the strengths and limitations of that mode of ventilation. This time I'm going to move on to talk about a major mode of ventilation known as bilevel pressure control. It's also known as BiPAP or DuoPap or Bivent. It has lots of different monikers because it's made by different manufacturers, but they're all essentially the same and they rely on a specific technology known as active exhalation. We'll discuss the setting up of bilevel and of course bilevel and its use for relatively normal lungs or mild lung disease in the ICU. And I'll return to a scenario that we used a little bit earlier on in the course. A patient who arrives in the ICU called Loretta, who you know nothing about. She just arrives intubated and sedated. You put her on a ventilator and you're asked what mode. Volume control, pressure control, volume guaranteed pressure control, assist control, SIMV. Is there an alternative? And there is. And that alternative is bilevel pressure control. Now what this is a pressure controlled mode of ventilation that looks just like SIMV pressure control except for the handling of the spontaneous breath. The spontaneous breath is either fully independent of the control breaths or it is synchronized with the control breaths. So this is not SIMV and it's not assist control. It's a different way of handling the spontaneous breaths. And that's what I really want you to understand. Assist control and SMV, the pressure control breaths are exactly the same. What makes them different is the spontaneous breath. On assist control, what you have is essentially a breath that is a semi-facsimile of the control breath because the time and the inspiratory pressure are the same. In SMV, you can sync in those breaths or the patient can get pressure support or be unsupported or get automatic tube compensation. In bilevel, you can have all of this, but you can have more at different levels of airway pressure. And the reason for this is that expiratory dissynchrony is abolished due to the presence of an active exhalation valve. A lot of ICUs use this as their default mode of ventilation. So when Loretta arrives in, she gets stuck straight on this mode of ventilation. It's done all over the world in all kinds of different ICUs as an alternative to assist control or SIMV. To understand what bilevel is, we need to go back in time to when this was a very modern technology. In tutorial 6 I mentioned intermittent mandatory ventilation or IMV volume control, but there is a pressure control variant. On this particular setup we have pressure control ventilation, inspiratory pressure of 15 centimeters of water with a PEEP of 5 that will give a pressure limit of 20. With a respiratory rate of 12, that's one breath every 5 seconds, and an inspiratory time of 1 second. The ventilator cycles time triggered and the patient gets a breath, and you'll see a standard decelerating flow breath with a flat top pressure waveform, and that's what the control breath looks like in IMV. Now the patient exhales by elastic recoil and we measure the exhaled tidal volume. This tidal volume, of course, is variable in pressure control. Now, if the patient wants to take a breath themselves outside the window of the IMV breath, then the breath is drawn from a bag that is on the expiratory limb of the breathing circuit. So they breathe in, they draw air from that bag, and they inflate their lungs. And so you see a typical sinusoidal waveform pattern of spontaneous breathing on the screen. And then of course they exhale the same way and we measure exhale tidal volume. So that's what happens with the spontaneous breath in IMV. And it looks like this on the waveform. We see a standard decelerating flow waveform and then the sinusoidal flow and pressure waveforms associated with spontaneous breathing. And in the original version of IMV, that spontaneous breath was not supported. The problem with IMV, of course, is that if the patient decides to take a breath while they've already got a lung full of gas, they will stack the breaths, and if they try and exhale, they will start bucking the ventilator. They'll become dysynchronous. Of course, the natural evolution of this was the SIMV version that I mentioned in a previous tutorial. And this is an interesting mode of ventilation. Again, it has controlled breaths, assisted breaths, and pressure-supported breaths. But what's curious about this is that even though the inspiratory pressure may be the same for all three breaths, the tidal volumes may vary. For the controlled breath, you will get the tidal volume that you anticipate, but if the patient assists the breath, just like in pressure control, the tidal volume will be greater because the driving pressure exceeds the inspiratory pressure. And then the pressure-supported breath can be anything depending on what level the pressure support is set at. In this particular picture, the pressure support inspiratory pressure is lower than the SIMV control pressure. It's extremely important to understand that the human diaphragm is the principal muscle of respiration. It works and wants to work continuously. It is a biological oscillator in the body, and it goes continuously generating a minute ventilation that is controlled by the carbon dioxide tension of cerebrospinal fluid. It can only be stopped by high doses of sedatives, particularly opioids and neuromuscular blockade. If disabled, the diaphragm becomes both atrophic and dysfunctional, and once it becomes dysfunctional, liberating a person from a mechanical ventilator becomes much more difficult. As a result of this, we tend to limit the use of neuromuscular blockade to fewer than 48 hours, if at all possible. Moreover, it's important to also understand that when we are delivering pressure and inspiration and holding it there, most of us wish to exhale after about 1.5 seconds, and that becomes problematic. Now, this is a situation where we have a patient on pressure assist control with an IP of 15, so the driving pressure is 15, the PEEP is 10, and the inspiratory time is 2 seconds, so very generous inspiratory time. Let's see what happens here. You can see that the patient has triggered the ventilator, and there's a terminal upstroke at the end of the breath. The breath actually finishes at the end of 2 seconds, but the patient is clearly beginning to exhale before the end of the breath. Note also that I've drawn a red line above that breath. That's where the P max has been set on this particular ventilator. That is the maximum allowable airway pressure. Above this point, the ventilator was cycled to expiration. This is expiratory dissynchrony in pressure assist control because the inspiratory time is too long for the patient. The breath is over as far as the patient is concerned and they want to exhale, but you as the operator want to give them that long inspiratory time in order to improve oxygenation. And we talked about that extensively in pressure control. In this situation, the patient has done the same thing. They trigger the ventilator cycled to inspiration, the same settings, but what's happened here is that the patient has exhaled in the middle of the breath, the pressure has gone above the point of the P max, and the ventilator has now cycled to expiration before the end of the set inspiratory time. So again, the breath is going on too long for the patient and they have pressure cycled the ventilator, and this is the major problem with all conventional pressure control modes. That's pressure assist control, SIMV pressure control, and volume guaranteed pressure control as they were originally configured. How this has been resolved was a technology that was introduced in the 1990s known as the active exhalation valve, and it looks like this. What this does is it maintains airway pressure. So if the airway pressure, for example, is at 20 centimeters of water and the patient decides to exhale, this valve partially opens, pressure is ventilated off. So think about that. It's like you open up a balloon and let a bit of gas out of it. A little bit of gas comes out and then it locks down again to maintain the pressure. So it actively opens and closes to keep that airway pressure where it needs to be so that you can give this patient a very long inspiratory time and they can exhale and indeed inhale because it keeps that pressure where it needs to be. Without active exhalation, you'll see the spontaneous efforts like this, and you see these spikes, and it's really ugly, and this is not good because the ventilator will either cycle to exhalation or the patient will start bucking the ventilator. With the active exhalation valve, it looks like this. The patient is really comfortable. And that is what bilevel pressure control is. It is pressure control ventilation as normal, but with an alternative pathway for supporting the spontaneous breath. So let's summarize this. Modern ventilators have a dynamic expiratory flutter valve that permits maintenance of airway pressure despite the patient inhaling and exhaling. The device flutters to maintain the pressure. The patient cannot become dysynchronous as they don't really synchronize. So this is a highly versatile pressure control mode that can be used in any patient in any setting. The flutter valve has solved the problem of expiratory dissynchrony. It solved the problem of IMV. So assuming that I convince you to use this mode, you go to your ventilator and you go, well, where is this? And the problem is that every ventilator has a different name for this mode of ventilation. A couple of them, GE and Puritan Bennett, call it Bilevel. Draeger calls it both BIPAP and PC pressure control, BiPAP. Avia call it biphasic. Hamilton call it DuoPap, and Macway call it Bivent. All of these are okay, and they sort of describe it, but I'm going to use the term bilevel pressure control. You can use whatever term you want, but I'm going to use this because it's how I've been calling it for many years. It's bad enough that the manufacturers all have different names for this mode, but then they also take what is basically pressure control ventilation and invent completely new terminology for things that already exist. So instead of calling PEEP, they sometimes call it P-low, low PEEP or low CPAP, all of which are okay. Then the pressure limit that we've talked about throughout this course is sometimes called P-high, which I think is okay, or high PEEP, which makes no sense, high CPAP, or P-insp. And more irritatingly, there is normally no terminology for the difference between PEEP and the pressure limit. That's what we normally call the inspiratory pressure. Now, I pointed out when I talked about pressure control that Draeger really don't do this. A simple approach that I'm going to use here is that I'm going to call the pressure limit the high airway pressure, and I'm going to call the PEEP or atmospheric pressure the low airway pressure. And it's important to understand that there are times when you will use this ventilator mode where you're not going to use PEEP. So we're going to call it high airway pressure, which is the pressure limit, low airway pressure, normally the PEEP. And it looks like this. So we have our low airway pressure, it's 10 centimeters of water. We have our high airway pressure, that is 25 centimeters of water. So the inspiratory pressure, or the driving pressure, is 15 centimeters of water, and that's our inspiratory ramp. And that gives us our tidal volume, which is hopefully 450 mils for our standardized patient. How bilevel pressure control works. In this cartoon, we have set the mode of ventilation as bilevel, with a P high of 20 and a P low of 5. That means a high pressure level of 20 and a low pressure level equivalent to PEEP of 5, and an inspiratory time of 2 seconds. As this is pressure controlled ventilation, the breaths are both time triggered and time cycled. The airway is inflated to tidal volume. In this case, we are targeting 450 mils. The pressure will be held for 2 seconds, but flow has stopped after less than half a second. That is controlled by the inspiratory ramp and the rise time. Keep an eye on the waveforms on the top right-hand side as we go through this sequence. 1 second has passed and the airway pressure is being held at 20 centimeters of water, and now the patient takes a spontaneous breath. Remember, there's flow triggering going on the whole time, so flow by is active all the time, and when the ventilator senses that the patient is taking a breath, it generates a flow of gas. The lungs will expand a little as there is significant inspiratory reserve volume, and this is reflected on the ventilator as a spontaneous breath. You will also notice that there's a small flow waveform and a divot on the pressure waveform. All this time, the airway pressure is still being held at 20 centimeters of water. Shortly afterwards, the patient begins to exhale. Lung volumes fall slightly and gas is vented off, but the ventilator keeps the airway pressure locked at 20 centimeters of water by a combination of fluttering of the active exhalation valve and flow through the circuit. The magic of this mode is how it does this. Note the presence of some negative flow on the waveform while the pressure waveform is locked in place. A small tidal volume will be registered on the ventilator. Once exhalation occurs at the end of the inspiratory time, the tidal breath flows out of the patient and the tidal volume can be measured. Let's look at the settings that you need to apply to use bilevel pressure control. The first thing you must do is set a high pressure level. This is the pressure limit, or the P-insp. This is the point above which you don't want the ventilator to generate positive pressure. The second thing is you set the low pressure level, or the PEEP, or atmospheric pressure, and of course the driving pressure is the difference between the low pressure and the high pressure. Then there's a whole configuration thing that you need to do regarding the respiratory rate, inspiratory time, and expiratory time. And you have three options. You set a rate and a time high, that's the inspiratory time, a rate plus a time low, that's the expiratory time, or you set a time high and a time low, and then the ventilator figures out the respiratory rate. You set an FiO2, the inspiratory ramp, or the rise time or the slope, the trigger, which is either pressure or flow, and if you're going to use it, the pressure support, inspiratory pressure level, and the expiratory sensitivity. Finally, like in all pressure control modes of ventilation, you need to set the P max, and it needs to be at a reasonable level because your patient can actually breathe spontaneously at the high pressure level, and you need to be careful that they don't overpressurize the system. Now this is the setup screen on Puritan Bennett ventilator, and we're going to choose the bilevel mode, and the spontaneous type here we're choosing pressure support, but you could use tube compensation. We're going to use a flow trigger, and there's the V-sense, just like in all of the modes that we've been using. And what you're going to set here is a P high. In this situation, it's the high pressure, the pressure limit of 20, and a P low, or the PEEP, of 5. And because it's a pressure control mode of ventilation, we're going to set a rise time here, 70%, and because we have a choice of pressure support or not, it's currently set at 0, but you can put on pressure support. You'll also set an expiratory sensitivity. Now what I left out here is how you set the inspiratory time, and there are several ways to do this on the Puritan Bennett ventilator. In this situation, you can set an I/E ratio, which is an elegant way of doing it, and I discussed this in a previous tutorial, that the advantage of an I/E ratio is that when you go up and down on the frequency, the relative ratio of inspiration to expiration doesn't change, so you don't end up with extremely short expiratory times and lots of dead space and auto PEEP. There are, of course, other ways of setting inspiratory and expiratory time. This is the conventional way you do this in pressure control, where you set the time high, or the inspiratory time, and then you let the ventilator figure out the expiratory time based on the respiratory rate. Alternatively, you can set an expiratory time, and the ventilator will figure out the inspiratory time based on the expiratory time and the respiratory rate. You can also set pressure support on this mode of ventilation, and it's important if you're going to set pressure support that you think about your end expiratory lung volumes. It would be conventional to only set pressure support at the lower pressure level, not the higher pressure level, although it is possible on some ventilators. Now let's take a closer look at the screen of a patient who is on bilevel. In the red box here, you can see that we have the basic settings, which are the high airway pressure level and the low airway pressure level. And on the screen there, that's the high pressure, and this is the low pressure. And they're the equivalent of the pressure limit and the PEEP. If you were to look at these two pictures side by side, you think, well, this is the same mode of ventilation. But in fact, on the left-hand side, we have a patient who's on pressure assist control, where the inspiratory pressure is set at 10 centimeters of water with an inspiratory time of 1.3 seconds. And on the right, we have a patient who's on Bilevel, and the high pressure is set at 15 and the low pressure is set at 5. So essentially the same driving pressure in both modes. It's just a different way of describing them, and this can be a little bit frustrating for people who are novices to this mode of ventilation because the nomenclature is different, but it really works the same way. And the reason why these two screens are pretty much identical is because the patients are not really interacting with the ventilator. And it's important to understand this, that when you put a patient on Bilevel, and if they're paralyzed, it's just pure pressure control. There is no difference. It's identical. Just the settings are just done differently, but it's pressure control ventilation with a rise time, with an inspiratory time, with an expiratory time, with PEEP, etc. Let's look at Bilevel on the Draeger ventilator. You can see here, Draeger call this mode pressure controlled BiPAP, and there's also a little thing saying pressure support. Now, I think BiPAP would be a great name for this mode of ventilation, except for the fact that everyone in the world thinks of BiPAP as a non-invasive pressure support mode of ventilation, which is obviously different from this. So even if I was using Draegers every day of the week, I would be calling this Bilevel. And the controls are here at the bottom of the screen. There's also a pop-up control screen like this, and they really make it very easy for you using this mode as a conventional mode of ventilation. With these settings, first of all, you set your respiratory rate, 15, then the PEEP, which they call PEEP, the inspiratory time, which in this case is 1.6 seconds, the slope, the P-insp, which, as you recall from our discussion on pressure control, is really the pressure limit. The driving pressure here goes from PEEP to P-insp. So if the PEEP is 5 and the P-insp is 15, that's a driving pressure of 10. At least it's consistent across Draeger pressure control modes. You also must set the P-max, or as I sometimes call it, the booking pressure. And that's it. If you want to adjust the expiratory time and go with extreme I to E ratios, Draeger have gone ahead and just made a completely different mode that they call APRV, airway pressure release ventilation, where you can make those settings. So they've really set this up as a conventional mode, something that patient comes in the door, you just put them on. It's time now to look at the pressure waveforms in Bilevel pressure control. And on this screen you can see on the left hand side we have two pressures. We have a low pressure of 5, that's the PEEP, and a high pressure of 20. And that's what we're going to be talking about, a pressure low and a pressure high. And the ventilator is going to time cycle from low to high, and it looks identical to pressure control ventilation. This is with a 1:1 I/E ratio, 1.5 seconds in inspiration, 1.5 seconds in expiration. So no different from any other pressure controlled mode. What makes Bilevel different from SIMV, from assist control, and from just standard pressure control with no assistance is what happens with the spontaneous breath. So let's let the patient breathe. And now this looks a whole lot different, doesn't it? Because we have two different breaths here that we haven't seen before. The first breath is that sinusoidal pattern that we associate with spontaneous breathing, and for all intents and purposes, at elevated airway pressure, this is CPAP. On the other hand, at the lower pressure level, the PEEP level, the patient takes a breath, and that is pressure supported. It doesn't have to be. It can just look like a CPAP breath, but on this setting here, we've given the patient pressure support. And indeed, if you make the inspiratory time quite short, it could look like this. And if you didn't look at the ventilator, you would think, wow, this is SIMV pressure control with pressure support. But the other thing, of course, you can do is make the breaths much longer. And here we are with pretty long breaths. And you can see here the patient is taking breaths at the top of the pressure, that's CPAP, but also they take a breath just before the ventilator cycles to the higher pressure level. And what happens there is the ventilator synchronizes the two breaths, a little bit like SIMV, that pressure assist breath. It's worth pointing out that if you're going to use Bilevel pressure control, that monitoring is difficult. often there is a very high apparent respiratory rate of 30, 40 or 50 breaths per minute, and the high respiratory rate alarm goes off. These are actually micro breaths, and the patient really isn't in any distress, they're just panting away. So you need to set that respiratory rate alarm up much higher than you would normally do. The screen waveforms are really ugly, and I've spent a lot of time in this course showing you different waveforms that you can analyze looking for patient ventilator dissynchrony. In this mode of ventilation, it's impossible to do that because the patient never really synchronizes and everything looks ugly. The pressure waveform looks ugly, the flow waveform looks ugly, the pressure volume curves, the flow volume curves, they all look ugly. You just got to live with it. And because the tidal volumes are highly variable, every little breath is measured, and a minute ventilation is more important than tidal ventilation on this mode. Nobody really knows what the end inspiratory lung volume is, and this is potentially problematic because there is a positive pressure deflection during inspiration at the high pressure level, and you have to be a little bit cautious about how you set that high pressure level. Now on this chart here I have the airway pressure on the y-axis, and I have two different pressures. I have a pressure low of 10 and I have a pressure high of 28. Above this I'm going to draw a 30 centimeter of water pressure line, and that's our red line. We don't want to go above that. Let's give the patient a breath. So they get their pressure control breath, and the patient takes a breath in the middle of that, and you can see that sinusoidal waveform pattern. Now what's important here is that positive pressure deflection on expiration will bump up the airway pressure. It usually does not exceed 2 centimeters of water. So in general, I don't set the high pressure level at more than 28 so that we don't push through that 30 centimeters of water barrier. From this, you can probably figure out that if you're treating a patient with acute hypoxic respiratory failure with bilevel ventilation, it's all about controlling the airway pressure, not controlling tidal volumes. If you want to rigidly control tidal volumes, you need to use volume control ventilation. Now let's move on and see what these look like actually on the screen. And this is a really good example of bilevel. The patient's on 20 breaths per minute with a high pressure of 25 and a low pressure of 8. The inspiratory time is 1.2 seconds. As you can see, there's a big mixture of breaths here. We have controlled breaths, we have assisted breaths, we have pressure supported breaths, and we also have breaths at the top of the Phigh that look just like CPAP. So they're unassisted breaths. Now one thing I will point out to you here is that the pressure support has been set at 7 and the driving pressure is 17 on the pressure control breaths, and that's why the pressure support breaths are so small in comparison. Just to show an example of a really long breath, someone who's got a really long inspiratory hold and the patient is breathing away spontaneously. This is the flow waveform here, and you can see this little bit of flow going in and out, and that mirrors above that on the pressure waveform some spontaneous breathing that looks just like CPAP. Finally, you can see here in this particular picture, this looks a whole lot like SIMV pressure control because every second breath is pressure supported with a pressure support of 10 versus the driving pressure of 18 for the pressure control breath. So, it's quite a versatile mode of ventilation, but its closest relative in the spectrum of modes of ventilation is SIMV pressure control. Well, what are the advantages of using bilevel pressure control? It is a pressure control mode that can be used on virtually any patient in the ICU. It resolves the problem of expiratory dissynchrony during long inspiratory times that we use for patients with severe hypoxic respiratory failure. It also allows unlimited spontaneous breathing that has 3 benefits. 1, improved oxygenation. 2, prevention of diaphragmatic atrophy. And 3, increased cardiac output due to improved venous return caused by the slight negative pressure that's generated in the thorax during those spontaneous breaths. And do not underestimate the value of this in terms of ventilation perfusion matching. The disadvantages of bilevel are that it's really confusing for practitioners used to other modes of ventilation, and I lay the blame for this completely at the manufacturers who use different names for this and their own nomenclature for simple things like PEEP and the pressure limit, and it's just really irritating, and even setting it up, particularly on the Puritan Bennett ventilator, is quite fiddly compared to other modes of ventilation. There isn't a lot of benefit proven from this mode, incidentally, outside of severe hypoxic respiratory failure, and even in that setting the data is not great. Moreover, there are often horrible waveforms on the screen, and sometimes this causes people to freak out and panic, particularly if the respiratory rate alarm has been set too low and the alarm is going off onk, 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 because the respiratory rate is 35 or 40 breaths per minute. And I'll just show you, this is the kind of typical screen you see with this particular mode of ventilation. And yes, it's really ugly, but that doesn't matter, because breathing is actually pretty ugly if you were to look at it from breath to breath, particularly if you, for example, monitored my respiratory pattern while I'm giving this tutorial. So let's review the tutorial. In this tutorial, I talked about bi-level pressure control and why it's a relatively novel mode of ventilation that's built on top of an active exhalation valve. It's very similar to pressure control ventilation, except for how the spontaneous breath is handled. I discussed how you set up bi-level pressure control, and I discussed the strengths and limitations of this mode. Next time I will move on to an extreme version of bi-level known as airway pressure release ventilation that has become very popular for the management of patients with acute hypoxic respiratory failure, otherwise known as ARDS. I'll talk about how you set up airway pressure release ventilation and a clinical strategy for how to use it and how to adjust it, and of course when not to use it. I'll see you then, and I guarantee you'll learn something. So that was bi-level pressure control. Next time, airway pressure release ventilation. If you're enjoying these tutorials, don't forget to subscribe on YouTube or follow me at ccmtutorials.org.